Hello, my name is Vitor Manfrinato. I'll be talking about the lithographic engineering of surface plasmons and volume plasmons. I'm from MIT. My advisor is Professor Carl Berggren. And I'd like to note that this was a team effort by my lab mates Richard Hobbs, Eugenia Young, and Sarah Goodman. And this work was also in collaboration with Brookhaven National Lab. So what I would like to study here is the engineering of UV and VUV resonance in nanostructures. UV stands for ultraviolet and VUV stands for vacuum ultraviolet. And the resonance that are within this range are basically the surface plasmons and volume plasmons. So a second goal would be we can divide this general goal in two. One would be high energy engineering of high energy surface plasmons. And another one would be to study and engineer volume plasmons and try to expand the domain of surface plasmons to volume plasmons. And I will explain to you what those resonance means. Basically, surface plasma, it's a collective motion of free electrons or valence electrons at an interface. So here you can see on the left, we have surface plasma polariton, and which is a propagating wave, let's say from the left to right here, polarization wave going in the interface. Another kind of plasma would be a localized surface plasma here on the right. And in here we have a dipole. There's a dipole induced by light or electrons. And these are, they don't propagate, they stay and keep oscillating in particles. These are the most common surface plasmas in condensed matter. And let's talk about volume plasmas. They are basically a collective motion of free electrons or valence electrons that propagate in the volume of a solid. Here I have a sketch from Ritchie, where you have, he put schematics of the atoms. So each circle here represents an atom, and each arrow represents a displacement of electrons, specifically the displacement of electron clouds. So what happens is that if you have an electron beam here, this red arrow, inside the material, what's going to happen, you're going to create an electric field that is going to excite, it's going to act in the electron cloud. So here he represents the electron cloud displacement, epsilon. And what constitutes the volume plasma is basically a polarization wave that propagates throughout the bulk of the material. And here he also represents the wavelength of this volume plasma right here. Then let's talk about interesting applications of the surface plasmas to start, which are the more conventional ones. Here you see on the top a single molecule sensor developed by this paper here, which basically means that you have a nanostructure, a rod, and you can keep monitoring the surface plasma resonance of this rod. And then if you have a single molecule attached to this rod at a certain time, t, what they show that they notice a shift in the surface plasma resonance. And this kind of technique can get down to single molecule sensitivity. So it's very interesting. Other interesting applications of plasmonics will be nano-optics. Here at the bottom, I show you in this paper from Akimov, they placed the colloidal quantum dot very close to a metallic rod, a silver rod. And then what they show is that they can couple the energy flow from the quantum dot to the surface plasma on the rod. And then the surface plasma on the rod can propagate. And at the end, it will decay. The surface plasma decay and generate light. So here on the right side, you can see the quantum dot is this red circle. And then by sending light to the quantum dot, by the exciton coupling from the dot to the surface plasmon, in the surface plasmon propagation of energy, you see that the end of the rod, there is it lights up. So this will be a very interesting application of, for example, sub-wavelength photonics, in case you could manage the losses happening from the surface plasma. So some recent topics on plasmonics, it's high energy plasmonics. So in this interesting work here from Naomi Halle's group, they show that you can achieve, you can tune the energy of the surface plasma from the visible down to the UV, down to 250 nanometers. And there's a lot of people looking for other different materials that could sustain surface plasmas to high energies or small wavelengths. Another interesting topic in plasmonics recently is the atomic scale plasmonics. Here on the right, I show you a work from this group in this paper here that they show different electric field enhancements between dimers by simulating atomistically these structures. So you see here in this dimer, depending on the arrangement of the particles, if you have two flat surfaces or you have one flat surface in a corner, you have quite different electric field enhancement, therefore different plasmonic resonance here. So when you are down to these atomic scales, to these really small scales, it's very important the feature size, uniformity, also pattern density. So you really need, there's I would say, a great need for high resolution, high precision nanofabrication. So going forward, let's talk about a little bit more on high energy surface plasmons here. Here I showed to you some interesting work from the literature that I found. Let's focus here on this work on the right, where on this group from Naomi Halle's, they published this work where they study surface plasmons in these rods. So you can see here that when you confine, you have a rod that is 100 nanometers by 40. So if you shine light along the narrow width of the nanorod, you excite high energy dipole surface plasmas up to 5 eV, for instance. And if you shine light polarized along the long dimension of the rod, you would excite lower energy surface plasmas. So to sum up, people have studied the surface plasma in different materials, and they have pushed it. The highest energy of the dipole localized surface plasma was about from 5 to 7 eV. Furthermore, people have also studied higher order localized surface plasmas. However, the energy is quite smaller, around 4 eV, the maximum energy reported. And people have also studied the effects of oxide thickness and particle shape, for instance. In this work, I would like to push plasmonic structures to the smallest length scales and see what will happen to the surface plasmons and the volume plasmons. So let's go it. The fabrication process here, it will basically use high resolution electron beam lithography. And the substrate that we're going to use, it's a silicon nitride. And we're going to use the PMMA as the resist. We're going to expose an area in the resist and develop, making a hole, for instance. And then after development, we're gonna use aluminum as the material here, because as I show you, aluminum is quite interesting for high energy surface plasmas, and aluminum is very interesting materials to observe volume plasma, because the volume plasmas are not highly damped in this material. So then we're going to perform aluminum evaporation and then liftoff, having at the end the substrate here, silicon nitride, and a aluminum nanostructure. I'm going to talk here mostly about discs, aluminum discs. Here's a 3D rendering of the final structure that we're going to have. It's going to be a very thin silicon nitride and aluminum discs on top of it with height from 15 to 20 nanometers. And we should note that there's some oxide on the aluminum here. So here we have a TEM image showing the smallest structures that we fabricated. We fabricated down to 6 nanometer aluminum nanodiscs. And we chose silicon nitride as a substrate because we're going to do TEM metrology and electron energy loss spectroscopy. So for TEM, we're going to choose use scanning transmission electron microscope to image our structures. This is a very well-established, really high-resolution technique that you can get down to the atomic scale. How it works is that you're going to have a focus beam on the sample, a convergent focus beam, and then the electron can go through without scattering or with small angle scattering, and the electron could suffer elastic high-angle scattering over here, which is around the angle theta 1. And if you try to collect the signal from this high-angle elastic scattering, you can use the high-angle annular dark field detector, and you can get quite high-resolution images. And we're going to get those signals to image our structures. And in order to collect the electron loss, we're going to collect more towards the center of the optical axis. So as I told you, we're going to use electron energy loss spectroscopy to map the surface plasma modes. The interesting thing of EOS is that you can study the plasmonic structures in individual particles. So there's no inhomogeneous broadening. You're not probing a lot of different particles with different shapes and different feature sizes. Another interesting thing from EOS is that you can excite a lot of different modes. You can even excite dark mode that is not going to be possible to see with conventional optical spectroscopy. So how it works? So here you have the substrate, silicon nitride, and the aluminum structure. I'm going to shine a focus beam that's going to go through the sample. And the electron that gets transmitted to the sample is going to have a certain energy loss. And we're interested in this energy loss. So here, at this point, at every point, I'm going to have a full spectrum of electron energy loss. And what is the standard in EOS? We're going to do a 2D map. So here I show you at the right a 2D map. So at every pixel here in this 2D map, I have one different electron energy loss spectrum or EOS spectrum. So I could see how the spectrum changes as a function of position or as a function of how close I am at the edge or the center of the particle. Some good EOS capabilities is that, again, we're going to achieve sub-nanometer spatial resolution. If you get good EOS system, you can get sub-electron volt energy resolution. And another very cool thing is that you can have wide energy range, so you can measure surface plasmas up to the volume plasmas at around 15 eV. So you can measure everything. Then here is a typical spectrum. We have electron counts on the y-axis as a function of electron energy loss. And here I show you 3 peaks. The first peak at 0 electron volts or 0 energy loss is what I call the zero loss peak. So all the electrons that are around this energy here, they didn't lose energy or they lose very small amount of energy. And you can see here around 5 to 6 eV, one surface plasmon peak, at 15 eV, the volume plasmon peak. So let's focus now on the surface plasma modes here. At the bottom, I show you again the EOS spectrum in the linear scale. Before, you should know that it's in the log scale. And here it's a surface plasmon peak. So let's study this resonance as a function of position. Here, surface plasmon, we're going to study one nanodisk. I show here you one stem image of a large nanodisk. And we acquired spectrum across this yellow line. And for example, we can get images and spectrums across this yellow line. Here I show you the image signal, the elastic scattered electron count as a function of distance. So you can see there's a small count of electron, which is the background, and then suddenly there's a sharp rise in the signal, and this is basically the edge of my particle. And then here in the top, is the signal of my aluminum disk. So one thing that I can do, I can first of all find where is the edge between vacuum and aluminum oxide, and also find the interface between aluminum oxide and metal aluminum. I can do this spectroscopically. So I found that at this point here, I am in the oxide-metal interface. And at this, from this point here is on distance at around 30 nanometers, I show you the spectrum at this point. So here is the electron count as a function of energy loss. And here again, at this wide peak that I cut off here is the zero loss peak. And here we can see 4 different surface plasma peaks. However, so we can get this spectrum, but it's a little bit difficult to figure out what is the physical nature of these different peaks. So for that, we performed a finite element method to simulate the charge distribution. The charge distribution or the induced charge induced in these particles with an electron beam excitation. So to do the simulation here, I show the setup. So what we simulated, there's a silicon nitride here. This is the substrate. And then we're going to simulate an electron beam going through it, just like an experiment. And here is aluminum oxide with 2.6 nanometers aluminum oxide. And then we can simulate, for example, here we can simulate the loss in the substrate, and the loss only in the aluminum disk, and the total loss. Here we see SP1, 2, 3, 4, and 5. We see from the simulation 5 different surface plasma peaks. But here still we cannot tell exactly the nature of these peaks. But because we did the simulation, we can also do a plot of the electric field normal to the surface. These are basically the surface fields that they indicate the presence of charge density. So here, this SP1 peak that I showed before, let's come back a little bit. For the SP1 peak at around 2.5 eV, and then this peak has this charge distribution. This is a dipole. And then if we go the SP2 peak, it's a quadrupole. SP3 peak is a hexapole. So now we understand more. These are localized surface plasma modes. And this simulation here is specifically for a diameter of 110 nanometers and 20 nanometers thickness. Furthermore, we also found some surface plasma polariton or waveguide modes that they are surface plasma modes that propagate in the cylinder, which we name it here SP4 and SP5. So now that we have an idea of how the plasma mode looks like, at least for large diameters, we would like to understand how these modes change as a function of feature size. So here I plot to you the surface plasma modes as a function of diameter. Here you see on the y-axis the surface plasma energy as a function of the diameter from 15 up to 120 diameters. So you see that before I show you the surface plasma energies experimental results and the simulations at around 110 nanometer diameter, here are they. You can see here the SP1, 2, and 3 mode and SP5 mode that we found experimentally. And then based on this modes as a reference, we tracked how these peaks changes, how they change as a function of diameter. You can see that SP1, 2, and 3, they tend to increase when we decrease the diameter. And SP5 and 4 mode, they tend to slightly decrease when we decrease the diameter. We also plot here the simulation to see if there's some agreement with that. And so here the continuous lines are the simulation of these different modes. You can see again from the simulation that SP1, 2, and 3, they tend to increase in energy when we decrease diameter. And SP4 and 5 modes, they tend to decrease in energy when I decrease the diameter. The bottom line here is that we show we basically show a wide control of the surface plasma modes as a function of lithographic feature size. So we can control the surface plasma resonance from down to 2 eV up to 8 eV. Furthermore, let's talk now more about the volume plasma modes in these structures. Here again, I show you the use spectrum, electron count as a function of electron energy loss. Here's the volume plasma at 15 eV, and here's the volume plasma image in the linear scale, again at 15 eV. So let's stop a little bit and look what people have studied in the literature, how people study and what is the behavior of volume plasmas as a function of feature size. Here from this paper is a nice reference that they tend to, they try to do a modeling of the volume plasma energy as a function of feature, and they gather a lot of different experimental results in germanium nanoparticles and nanowires. And they gather also data from silicon and bismuth across the literature. And you can see here that you can only see a change in the volume plasma energy only when you go with features smaller than 30 nanometers. So you can see a small change here in germanium when you are in feature size smaller than 20, and here in germanium nanoparticle 2. So it's very challenging to change the energy of the volume plasmas with feature size. Furthermore, there's some interesting work from Batson that he studied aluminum nanoparticles. Recently, have been some other interesting works where people study volume plasma in magnesium thin films down to the atomic scale. And also, people have used the volume plasma resonance to map temperature in aluminum nanostructures. So to sum up the results in the literature, volume plasma could be controlled only at the sub-30 nanometer scale. We have not found available top-down control, such as with lithography, in order to use lithography to control these resonances. We've seen very limited energy control, about 1 eV of energy shift when you have the volume plasmas confined. Furthermore, because of this limited data, there's some uncertainty on the reason of why this happens. So here we try to study that again using I already showed you the lithographic method to pattern these structures, and we're gonna do with EELs. So we're gonna do volume plasma mapping with EELs. So here is one example of one structure that we study. This is a stem image before EELs, and in the middle, there's a stem image during EELs. Again, we took about 1 to 2 nanometer step size, so in each pixel here, I have one spectrum, and then I can process each different spectrum in order to select the different resonance modes. So here, I perform the following processing. I basically am plotting you here just the volume plasma signal without any background. So with background subtraction and plotting the integral of the signal from 13 to 17 eV, I can get what I call here the volume plasma map, which is here. So one interesting thing that you can see here right away is that the difference between the volume plasma map and the image will be due to the silicon oxide signal. One thing that I did not tell you is that the volume plasma signal for aluminum is 15 eV, but for aluminum oxide, it's around 20 eV. So you can easily distinguish the signal from the metal and the oxide. So we did that so we can isolate the metal part and the oxide part. Therefore, we estimated from the measurements here that the aluminum oxide thickness is about 3 to 4 nanometers in these structures. And I show here is the core diameter, or just the aluminum metal diameter. And I'm mostly going to talk about the volume plasma behavior as a function of this core diameter. So let's study first the volume plasma within one nanostructure, and then we'll see how it behaves as a function of different nanostructures with different size. So here I have on top left a STEM image again, and the volume plasma map, as I explained you before. And we also plotted here the surface plasma map. This is the SP1 mode. And you can see that the mode kind of extends beyond the particle. On the bottom left, we have the normalized electron count as a function of beam position. So by looking at this cross-section here pointed in the middle of the particle, we plotted the intensity of the surface plasma in red right here, and the intensity of the volume plasma in black here. What you can see here is that the volume plasma signal is minimum at the aluminum oxide, aluminum metal interface. And at the same time, the signal of the surface plasma is maximum. So a key characteristic of the boundary effect is that you would have the surface plasma decrease once you get inside the particle, and the volume plasma increase. There's a trade-off between these two signals. And in the literature, people call this the boundary effect. However, other interesting thing that happens at this interface is that the volume plasma energy and full width of maximum changes. So let's go now on this bottom right graph. Here I have the volume plasma energy in black in the center of the particle. When you get to the edge, the volume plasma energy tends to increase. So it's increasing from 15.1 up to 15.2 eV. And the same behavior also happens for the volume plasma full width half maximum. You can see from the center to the edge, the full width half maximum is changing from 1.3 eV up to 1.5 eV, more or less. So this is another key signature of the boundary effect, and this happens throughout all the structures that we analyzed. So let's keep that result in mind, and now take a look of how the volume plasma changes as a function of feature size. So we changed the diameter from 18 nanometers down to about 8 nanometers, and we acquired the yield signal very close to the center of these particles. So here you have, let's talk about the signal of the volume plasma. You have volume plasma intensity divided by the total intensity on the yield spectrum as a function of aluminum core diameter. You can see that we can significantly change the intensity of the volume plasma excitation by decreasing the core diameter from 14 down to 3 nanometers. If you plot this, so this is the plot. If you try to fit this data that we did here with this dashed line, we found that the fit crossed the zero at 1 nanometer diameter. So we extrapolated from this experimental data set that we should not observe volume plasmas for particles that have 1 nanometer diameter of aluminum. So that's one interesting result from that. And now let's see how the volume plasma energy changes as a function of feature size. Here I show again aluminum core diameter from 14 down to 3 nanometers as a function of volume plasma energy. You can see that the data is quite scattered, but we see a certain trend to increase in energy from about 15 eV up to about 15.2 eV, 0.2 eV in increase. Slightly dependent on diameter. And in order to try to understand this data set, we performed a simulation based on this paper here that they study the non-local volume plasma modes. And basically, they also study the higher order volume plasma modes in nanostructures. So basically, the core of the simulation is that you have to consider the volume plasmas as standing waves inside the diameter, and they provide relationships of different volume plasmas with different wave vectors. So this here I simulated the 3 lowest order modes of the volume plasmas, and we see a relatively good agreement between them. And one thing that this suggests is that in these aluminum nanoparticle and nanocylinders, we may have excitation of only low order volume plasma modes. So this is an interesting result. Furthermore, we see here now the volume plasma full width F maximum, the width of the excitation as a function of core diameter. We see a much bigger change, a much bigger modulation of full width F maximum as a function of diameter. You can see the width change from about 0.9 eV up to 1.5 eV, much more than the resonance energy. And one way to model that is that we use a size-dependent dielectric constant to explain this behavior. And by using this size-dependent dielectric constant outlined in this paper here, we have a standard formula on plasmonics. So you have the full width F maximum as a function of radius, depends on the full width F maximum at the bulk, plus an extra factor that depend on the effective electron mean free path. And we achieve a reasonably good agreement with the data. So we believe that this classical model of the size-dependent dielectric constant might explain the volume plasma in our system. Furthermore, from the full width F maximum, we could calculate the volume plasma relaxation time. So the volume plasma relaxation time is the time that the volume plasma will decay by 1 over E. So it's a time that the volume plasma intensity the amplitude would decay by 1 over E. So by using this formula here on the right, the relaxation time is equal to h bar omega divided by the volume plasma full width F maximum that we measured experimentally. So here we plot you the relaxation time in the attosecond time scale as a function of aluminum core diameter. What we can see here is that we're tuning the volume plasma relaxation from about 450 attoseconds up to 700 attoseconds. So one thing here is that volume plasma, they tend to decay really fast. And another interesting thing is that if we have a linear fitting in this data set, we got a slope of 19.4 attoseconds per nanometer. So this means that if we're able to control the feature size with 1 nanometer precision, we will be able to change the volume plasma relaxation time or the dephasing time by 19 attoseconds. So we suggest that probing volume plasma lifetimes or relaxation times in these nanostructures might be very interesting for attosecond science. So to conclude, here we show a way to do by using high resolution patterning to extend surface plasmas to high energy. So we show some high energy surface plasmonics. And we also show some lithographic control of volume plasmas. That will be maybe one first step towards volume plasmonics. We also show that if you are able to tune, if you are able to pattern nanostructures at really small length scales, smaller than 3 nanometers, you might be able to remove, to suppress tremendously the volume plasma excitation. So that might be interesting to reduce electron and X-ray losses in structures. Furthermore, I show that by using basically by controlling the volume plasma resonance, we are controlling VUV resonance. So in this paper here on the right, on book from Redder and in other papers, people have shown that by specific conditions, you could control, you could achieve volume plasma excitation with VUV light. So here you see some excitation of volume plasma modes in silver thin films at around energies a little bit higher than 3.8 eV. So it might be in principle be possible to excite volume plasma not only with electrons and X-rays, but with high energy light. And if we're able to control the volume plasma resonance, we'll be controlling VUV light matter interaction. Furthermore, we show by studying the volume plasma Hall effect maximum that we're controlling the dielectric constant, the bulk dielectric constant, by using sub-10 nanometer lithography. Then I would like to close that some unique advantage by doing all this study with lithography is that you could, for instance, control your structures with arbitrary shape, because you're not limited by just cylinders or just rods. You can write whatever structure you want and study surface and volume plasma modes there. You can change different materials too. Furthermore, you could, for example, pattern structures that are really close together, high density structures, in order to engineer UV and VUV metamaterials. And in this case, you not only get an effective dielectric constant by putting structures close by, but by doing really high resolution patterning, you could control even, you can locally modify the dielectric constant, adding another degree of freedom for metamaterials. Furthermore, by using really high resolution lithography, you can see the transition from surface plasma and volume plasmas in bulk down to close to the atomic scale by using some specific fabrication methods, like we showed before. Then I would like to acknowledge my the supporters, the Center for Excitonics, Brookhaven National Lab, and Gordon and Betty Moore Foundation that support this work. And I would like to acknowledge people from Portuguese University, Marlene Lagos, and Philip Batson that help us to understand the system. I would like to acknowledge Jim Daly, Mark Maldo, and Young Zhang from MIT for helping us with the experimental setups. And I would like to acknowledge also my lab mates in Carl Bergen's group. So thank you very much.